Hello students, I welcome you in today's session of physics, and in physics as you can see here I am going to present your chapter number 6, which is your pressure in fluids and atmospheric pressure. Clear? So students, before going to start the chapter, just have a look what we have to study, the syllabus. So in this syllabus you can see there is a written that change of pressure with depth, which is including formula H rho G. Fine. Then transmission of pressure in liquid, atmospheric pressure. After that you have to cover out scope, that is thrust and pressure and their units. Pressure exerted by liquid column, which is P is to H rho G, derivation of P is equals to H rho G, and simple daily life examples like broadness of the base of a dam. Clear? Then driver suit, etc. Some consequences of H rho G, transmission of pressure in liquids, Pascal law, examples, atmospheric pressure, laboratory demonstration, common manifestation and consequences. Then you have to study about the variation of pressure with altitudes, qualitative only. Mention applications such as weather forecasting and altimeter, simple numerical problems on H rho G. Clear? So here you can see the first topic is your pressure in fluids and its transmission. Clear? So we will start with thrust and pressure. What is thrust and pressure? So first we talk about what is thrust. So a force can be applied on a surface in any direction. When the force is applied on a surface in a direction normal to the surface, then it is called the thrust. Clear? So a body when placed on a surface exert a thrust on the surface which is equal to the weight of the body. Clear? The thrust is the same in whatsoever way the body is placed on the surface. So the thrust is defined as, here this is the definition of thrust, the force which is acting normally on a surface is called thrust. Clear? Now thrust is a vector quantity. I hope you are familiar with the scalar and the vector quantities, but for your kind information I am telling you what are scalar quantities. So scalar quantities are those quantities which have magnitude only. Clear? Like time. Fine, distance. So these are the scalar quantities. Now if we talk about what are the vector quantities, so the quantities which have magnitude as well as direction are called as vector quantity. Clear? Now here you can see what is the unit of thrust. So it is measured in the unit of force. So the SI unit of thrust is Newton. You know very well the unit of force is also Newton. Clear? And the CGS unit of the thrust is dyne. So you can see the relation between the Newton and dyne. This is the important one, and just remember it, 1 Newton equals to 10 to the power 5 dyne. Clear? The gravitational units of the thrust is MKS system is kgf, and in CGS system is gf. So they are related as 1 kgf equals to how much? 9.8 Newton, and 1 gf is equals to 980 dynes. Now if we talk about pressure, so the effect of thrust depends on the area of the surface on which it acts. So the effect of thrust is less if it is act on a large area, while it is more if it acts on a small area. Now here you can see there is an example given here. If you stand on a loose sand, your feet sink into the sand. But if you lie on that sand, your body does not sink into the sand. Clear? So in both the cases the thrust exerted on the sand is same, equal to the weight. So when you lie on a sand, the thrust acts large area, but when you stand, the thrust acts on a small area. Clear? So the effect of thrust is expressed in terms of thrust per unit area, then it is called as the pressure. So you can see the definition, the thrust that on unit area of the surface is called the pressure. Clear? And what is the thrust? We had already discussed. The force which is acting normally on the surface is called thrust, and when it is acting over a unit area, then it converts into the pressure. Clear? So this is the basic difference between pressure and thrust. So if a thrust, that is F, act on area A, then you can write the relation between pressure and force by area. So P is equals to F by A. Pressure is your scalar quantity. I told you scalar and vector. Now what are the factors which are affecting the pressure? So the pressure exerted on a surface, it depends, first one the thrust, and the second one the area on which the thrust is applied. So here you can see the example given here. A brick of weight 4 kgf having the dimension of 10 and 5 centimeter exerts maximum pressure on the ground when it is placed with its minimum pressure on the ground when it is placed with 5 centimeter wide vertical. So here you can see the two positions of the brick is given. One is the horizontal position and the other one is the vertical position. Clear? And they are calculating the thrust and the area of the base is this, then you can calculate with the help of pressure using these two entities. Fine. So the thrust comes out to be, and then in the second case means you have to calculate the thrust in both the cases or pressure in both the cases, that is one in the horizontal position and the other one in the vertical position. So you can see that in the first case the pressure comes out to be 0.08 kgf per centimeter square, and the second case it is 0.02 kgf per centimeter square. So the pressure on the ground in the figure 6b, which is in the horizontal position, is 1/4 of the pressure in the vertical position. So obviously larger the area on which a thrust acts, less is the pressure exerts. Fine. Now the pressure on a surface is increased by distributing the thrust on a smaller area of surface. So for example, the ends of nails or a pin are made pointed so that the pressure is exerted at the ends of the ends and they can be driven into with a less effort. Clear? So the cutting tools also have either sharp or pointed edges so that the smaller thrust may cause a greater pressure at the edges and cutting can be done with less effort. So similarly, the pressure on the surface is reduced by distributing the thrust on a larger area of the surface. So for example, wide wooden sleepers are placed below the railway track so that the pressure exerted by the rails on the ground become less. Buildings have the wide foundation so that the pressure exerted by the building on the ground become less. So now we are calculating the unit of pressure. This is the unit of pressure you can see here. So from the relation you know very well, pressure is equals to thrust upon area, or you can say that the perpendicular force is called the thrust. So we can write it like pressure is equals to thrust by area. So its units comes out to be unit of thrust upon unit of area. So the SI unit of thrust is Newton and that of the area is meter. So the SI unit of pressure is Newton per meter square and it is abbreviated as Newton per meter square. So this unit is named after Pascal. So after the name of the scientist Pascal, we define Pascal as follow. 1 Pascal is the pressure which is exerted on a surface of area 1 meter square by a force of how much? 1 Newton acting normally on it. That is 1 Pascal is equals to 1 Newton per meter square, and the CGS unit of pressure is dyne per centimeter square, where 1 dyne per centimeter square is equals to 0.1 Newton per meter square, or 1 Newton meter per square is equal to 10 dyne per centimeter square. So however, if thrust is measured in kgf and area in meter square, the unit of pressure is kgf. So the thrust is measured in meter gf and area in centimeter square, the unit of pressure is gf per centimeter square. So other unit of pressure are bar and millibar, and this you can see the relation 1 bar equals to 10 to the power 5 Newton per meter square and 1 millibar equals to 10 to the power minus 3 bar, or you can write it 10 to the power 2 Newton per meter square. The atmospheric pressure is generally expressed in terms of the height of the mercury column. So at normal temperature and pressure, the barometric height is 0.7 mm of Hg, or you can write it 760 mm of Hg. So at the sea level, which is taken as 1 atmosphere. So the atmospheric pressure is also expressed in unit atmosphere, where 1 atmospheric is 0.76 mm of Hg, that is equals to this in Pascal. So sometimes we use torr as a unit for measuring the atmospheric pressure. So what is the relation between torr? So 1 torr equals to 1 mm of Hg. Clear? Now we will discuss about the pressure in fluids. So a substance which can flow is called fluid. You know very well. So that is all liquid and gases are fluids. So a solid exerts pressure on the surface due to its weight. So similarly, a fluid also exerts pressure due to its weight. A solid exerts pressure only on the surface on which it is placed, but a fluid exerts pressure on the bottom as well as on the walls of the container in which it is enclosed due to its tendency to flow. So you can see here a fluid exerts pressure in all the directions. So in other words, a fluid contained in a vessel exerts pressure at all points in all directions. Clear? Now there is an experimental demonstration given here, so I am skipping this and moving to the pressure exerted by liquid in a column. This was the important one, which is P is equals to H rho G. So you can see here, this is the figure, and with the help of this figure you can easily understood what I am going to teach you. Let us suppose a vessel which is containing a liquid of density how much? Rho. The liquid is density is how much? Rho. In order to calculate, and we are supposing that the liquid is in a stationary position in this vessel. So in order to calculate the pressure at depth, so let us consider the horizontal circular surface PQ. You can see here from this figure, this is PQ, which area is capital A and at a depth of how much? H, below the free surface XY. This is your free surface above XY. So for this, let us assume a cylinder PQRS whose height is small h with PQ as its base and top face RS lying on the free surface, that is XY, of a liquid. So from this figure, the total thrust which is acting on the surface PQ will be equal to the weight of the liquid column, that is PQRS. So the thrust exerted on the surface PQ, that is weight of the liquid column, is PQRS, and the volume of the liquid column PQRS multiplied by density multiplied by gravitation, acceleration due to gravity. So you know very well what is the volume of liquid column, that is the area of the base into height. So you can put the value area in place of area A multiplied by h, and you also know very well that is the density is rho and g is the acceleration due to gravity. So finally it comes out to be AH rho g. Clear? So this thrust is exerted on the surface, that is PQ of area A, therefore the thrust exerted per unit area, we can write this formula P is equals to force by area. So in place of thrust or force, you can put this value, that is AH rho g. So A and AR cancel out, and finally you will get pressure equals to H rho g, that is depth. Pressure is equal to depth into density of liquid into acceleration due to gravity. Clear? Now what are the factors that is affecting the pressure at a point in a liquid? So here you can see there are the few factors. From the above figure or equation number 6.2, this one, it is clear that the pressure at a point inside the liquid depend directly on the following three factors. The first one is the depth of the point below the free surfaces. The second one is the density of the liquid, which is rho, and the third one is the acceleration due to gravity, which is g. So at a particular place on the earth's surfaces, the acceleration due to gravity, that is g, is constant. Therefore the pressure at a point in a liquid is directly proportional to the depth, that is h, of a point from the free surfaces of the liquid, and the second one is directly proportional to the density, which is rho, of the liquid. So the density of sea water is more than the density of the river water. So pressure at a certain depth in sea water is more than that of the depth in the river water. However, the pressure inside a liquid does not depend on the shape and size of the vessel in which the liquid is contained. Now the second, the area of the surface in which it acts. So it should be remembered that to find the total pressure in a liquid at a depth, we must also take into consideration the atmospheric pressure acting on the free surface of the liquid. So if the atmospheric pressure acting on the free surface of the liquid is P naught, then it is taken into account, then you can write it, total pressure in a liquid at a depth h is equals to atmospheric pressure plus pressure due to liquid column. So you can write it P naught plus H rho g. This equation is 6.3. I hope you understand. So it is noticed that the gas bubbles formed at the bottom of a lake rises, it grows in sizes. Clear? The reason is that when the bubbles is at the bottom of the lake, the pressure exerted on it is the atmospheric pressure plus the pressure due to water column. So as the gas bubbles rises, the pressure exerted on it decreases. Now using the Boyle's law, you know very well PV is equals to constant. So the volume of the bubbles increases due to the decrease in the pressure, that is the bubbles grow in size. So when the bubble reaches the surface of the liquid, the pressure exerted on it become minimum equal to the atmospheric pressure only, and the size bubbles become maximum. Now this is the important laws of liquid pressure. So kindly pay attention, student. Following are the 5 laws of liquid pressure. The first one is pressure at a point inside a liquid increases with the depth from the free surface. It means if you go inside the liquid or a very high depth, deep into the sea or a river, then the pressure is increases. The second one, pressure is same at all points on the horizontal plane, that is in a stationary liquid. The third one, pressure is same in all direction about a point in the liquid. The fourth one, pressure is same depth in different liquids, it increases with the increase in the density of the liquid. Now the fifth one, a liquid seeks its own level. Now here you can see there are some consequences of liquid pressure, which is P is equals to H rho g. Why? What are the consequences? So first one you can see here, this is the important one, why the walls of the dam is made thicker at the bottom. Clear? So just see the figure number 6.3. You can see here below the figure 6.3, this one, this is the figure of a dam. So the figure this shows that the side view of a dam, its wall is made thicker near the bottom. The reason is that the pressure exerted by the liquid increases with its depth. As I told you, that pressure is increases as you go into the depth. So thus more and more pressure is exerted by the water on the wall of the dam as depth increases. So a thicker wall is required to withstand with a greater pressure. Therefore, the thickness of the wall of the dam increases toward the bottom. So in figure 6.3, the increasing length of the arrow shows the increase in the pressure on the wall of the dam, that is downward. Now come to the second one. Water supply tank is placed high. So to supply water in a town or a colony, the water supply tank is made in a sufficient height. Why? The reason is that the greater the height of the tank, more will be the pressure of the water in the tap of a house. Fine. So thus for a good supply of water, the height of the supply tank must always be a few meter high than the level at which the supply of water is to be made. Clear? So I am skipping this, the diverse rule, just read it by yourself, and if you still feel any doubt, you can ask me in the comment section. I am moving to the transmission of pressure in the liquid, that is the Pascal law. So we have read that the pressure at a point in a liquid which is density of rho and a height h. Clear? Below its free surfaces, that is P is equals to h rho g. So obviously the pressure difference between the 2 points in a stationary liquid depends only on the difference in the vertical height of a free surfaces from these points. Now if by some means the pressure at one point of the liquid is increased, so the pressure at all other points of a liquid must also increases by the same amount, so that the pressure difference between the two given points may remain same. This is the Pascal law. It can be stated as follow. You can see here, this is the Pascal law. So what's the Pascal law? State that the Pascal law states that the pressure exerted anywhere in a confined liquid transmitted equally and undiminished in all the direction throughout the liquid. So this can be demonstrated by the experiment, and this is the experiment. And you can see here the experiment. In this experiment, we take a glass flask having a narrow tubes which is coming out from its side and bottom. So the flask is provided with an airtight piston in its mouth, this one. You can see the figure number 6.4. So fill the flask with water. The water in each tube will be at the same level as in the flask. The initial level of the water in each tube is shown by the dotted thick lines. Now push the piston down the flask gently. It is observed that the jets of the water rises from each of the tube, reaching the same height, which is shown by the dotted lines from this figure. This shows that the pressure applied in the enclosed liquid is transmitted equally everywhere inside the liquid in all direction. Clear? Now what is the application of Pascal law? So here you can see application of Pascal law. So hydraulic machines such as hydraulic press, hydraulic jack and hydraulic brakes are based on the principle of Pascal law, that is transmission of pressure in liquids. So here we discuss about the principle of hydraulic machine. What is the principle of hydraulic machine? Clear? So student, this thing we will discuss in our next lecture. Till that you do study. So thank you class. Thank you very much.